Hi everyone, welcome back to Stanton 101's Calculus AB series with Eric Lee. Today let's take a look at the 2014 AP Calculus AB FRQ. Question 1 reads, grass clippings are placed in the bin where they decompose. For the interval 0 to 30 inclusive, the amount of grass clippings remaining in the bin is modeled by the function a of t, where a of t is measured in pounds and t is measured in days. Part A wants us to find the average rate of change of A of t over the interval from 0 to 30 inclusive and to indicate the units of measure. So we know from past videos in this series that the average rate of change of a function is just the slope of the function over its interval. So for part A, all we need to do is use the slope formula. So this is A of 30 minus A of 0 divided by 30 minus 0, which if you plug into a calculator gives you around negative 0.197. Our units of measure would be the units of A of t, which are pounds, over the units of just t, which is days. So our final units is pounds per day. Question B asks us to find the value of a prime of 15, and using the correct units, interpret the meaning of this value in the context of the problem. So remember that question 1 on the AP exam is a calculator question. So for part B, all we need to do is insert the value of a of t into our calculator, and then use the derivative function to evaluate its derivative at t equals 15. And doing that, we get a prime of 15 is equal to somewhere around negative 0.164. So what does this value mean in the context of the problem? Remember, the derivative of a function, in this case the derivative of a of t, shows whether that function is increasing or decreasing. Here, because the derivative of a of t is negative, we know that a of t is decreasing. And because a of t models the amount of grass clippings remaining in the bin, we can conclude that at time is equal to 15 days, the amount of grass clippings in a bin is decreasing at a rate of 0.164 pounds per day. Part C deals with the integral application of finding average values, which we will not cover for the sake of this 2020 exam. Part D asks us for t is greater than 30, L of t, the linear approximation to A at t equals 30, is a better model for the amount of grass clippings remaining in the bin. Use L of t to predict the time at which there will be 0.5 pounds of grass clippings remaining in the bin. Show the work that leads to your answer. So beyond all the fancy language like linear approximation, what this part is basically saying is after t is greater than 30, the equation we had previously been using, a of t, no longer models the relationship as well. Instead, they want us to use the new linear function, L of t. So graphically what's happening, and let me draw it off to the side, is that from t is equal to 0 to 30, we had used the function a of t. That's an exponential function to model the relationship we're looking for. So a of t looks something like this, an exponential relationship. As soon as we go over t is equal to 30, however, it wants us to switch gears and use a linear function to model the relationship. So from here, it looks something like this, where this is L of t, and this was A of t. Now let me move this graph down here. down here so we can work on this problem. So in order to use L of t, we have to find it first. We know that L of t is a linear function, meaning that we can model it in point-slope form. The easiest point we can use is the transition point at t is equal to 30. Because we know that at this point, the y value is equal to just a of 30, and the x, or rather the t value, is equal to 30. Now for the slope, if we look at this graph, we can see that the line L of t seems to continue on from where a of t was at t equals 30. So in other words, you can think of it like the line L of t continues on with the same slope that a of t stops with. So we know that the slope of L of t is just equal to a prime of 30. So now we can write this in point slope form. L of t minus the y value a of 30 is equal to the slope a prime of 30 times x, or t, minus the t value, minus 30. And we can rewrite this as L of t is equal to a prime of 30 times t minus 30 plus a of 30. Using our calculators, we can find that a prime of 30 is equal to negative 0.056 times the quantity t minus 30 plus a of 30, which is just 0.783. And all of this is equal to L of t. The question wanted us to find when the amount of grass clippings is 0.5 pounds. In other words, the question is asking us, when does L of t equal 0.5? So we set 0.5 equal to this quantity here. And this basically devolves into an algebra problem. We can solve for t to get t is equal to 35.05 days. Question 3 reads, the function f is defined on the closed interval from -5 to 4 inclusive. The graph of f consists of 3 line segments and is shown in the figure above. Let g be the function defined by g of x is equal to the definite integral from -3 to x of f of t dt. Part A asks us to find g of 3. So we know for part A that the x value is 3. So we just plug the value into our definite integral. So this would be the definite integral from -3 to 3 of f of t dt. We know that this definite integral here is just the area under the graph of f from x equals -3 to x equals 3. So the area we're looking for is just this blue shaded region. So our positive area is a 4 by 5 triangle, so that would be an area of 10. And then subtracted from our negative area, which is just our 2 times 1 triangle here, which is just 1. So g of 3 is equal to 9. Part B asks, on what open intervals contained in -5 to 4 non-inclusive is the graph of g both increasing and concave down? Give a reason for your answer. So remember that the definition of increasing is the first derivative, d dx, is positive. And the definition of concave down is when the second derivative is negative. So because we know that g of x is equal to the definite integral of f of x, then we know that f of x is actually the derivative of g of x, because the definite integral is basically just an antiderivative. So we can write that g prime of x, g's first derivative, is equal to f of x. Meaning for g to be increasing, f of x has to be positive. Has to be positive. Likewise, we know that g double prime of x, the second derivative of g, is equal to f prime of x. So that means in order for g to be concave down, f of x's slope has to be negative. So now all we need to do is look at the graph of f and find when f of x is positive but has a negative slope. So if we look up here, we can see that from -5 to 2, the graph of f is positive, but the slope of f is negative on the intervals from -5 to -3 and 0 to 2. So we know that for part B, the graph of g is increasing and concave down on the open intervals from -5 to -3 and 0 to 2. And our reasoning would be, because at that point f of x's slope is negative, or f of x is decreasing, and f of x is positive, meaning the first derivative of g is positive. Part C asks us, the function h is defined by h of x equals g of x divided by 5x, and it wants us to find h prime of 3. So we know when we take the derivative of a fraction, we have to use the quotient rule. So because we're given, for part C, we're given h of x is equal to g of x divided by 5x, to find h prime of x, all we need to do is apply the quotient rule to the right side. So the quotient rule states you keep the bottom first, so 5x, and you multiply it by the derivative of the top. In this case, this would be g prime of x. And you subtract this from, now you keep the top, g of x, multiplied by the derivative of the bottom, which is just 5. And this is all over your denominator squared. So this is 5x squared. So now we can evaluate this at x is equal to 3. So we know that this becomes 5 times 3 times g prime of 3. Now we know that g prime is just f. So this is f of 3 minus g of 3 times 5. And this is all over 25 times 9. Now, if we look back at the graph, we can see that f of 3 is equal to -2. And we know that g of 3 is equal to 9. So now we just plug in -2 for f of 3, and then 9 for g of 3. So now this just becomes -30 minus -45 is -75, and then 25 times 9 is just 225. And this simplifies down to -1/3. Part D reads, the function p is defined by p of x is equal to f of x squared minus x. Find the slope of the line tangent to the graph of p at the point where x is equal to -1. So we know that the slope of a tangent line is just equal to the instantaneous rate of change of the graph at the point where they intersect. So all we need to do for part D is to take the derivative of p of x and evaluate it at x is equal to -1. So we know that for part D, p of x is equal to f of x squared minus x. When we take the derivative of p of x, so p prime of x, the chain rule kicks in for the right side. So first we need to take the derivative of the outside function. The derivative of f of x squared minus x is just f prime of x squared minus x. And the chain rule states we multiply this by the derivative of the inside function. So the derivative of an x squared is just 2x, and then the derivative of a minus x is just -1. And this should be in parentheses. So now let's evaluate this at x is equal to -1, the point at which the graph and the tangent line intersects. The value of this first factor here would just be f prime of the quantity -1 squared is 1 minus the -1 is 2 times the quantity 2 times -1, which is -2, minus 1. Now we know that f prime of 2 is just the slope of f at x is equal to 2. And this is -3. So let's rewrite this as -3 times f prime of 2. So now if we look at the graph of f, the slope at x is equal to -2 is just the rise over the run. So that's -4 divided by 2 is -2. So the value of f prime of 2 is just -2. So this is equal to -3 times -2, which is equal to a positive 6. So now let's take a look at question 4. Question 4 reads, train A runs back and forth on an east-west section of a railroad track. Train A's velocity, measured in meters per minute, is given by a differentiable function VA of t, where time t is measured in minutes. Selected values of VA of t are given in the table above. Part A asks us to find the average acceleration of train A over the interval 2 to 8 inclusive. So we know that the average acceleration of this train is just the average rate of change of the velocity with respect to time, which is just what we can find using the slope formula. So using the slope formula, the velocity at time t equals 8 is -120 minus the velocity at time t equals 2, which is 100, divided by 8 minus 2. And this equals -220 over 6, which is -110 over 3. Part B asks, does the data in the table support the conclusion that train A's velocity is -100 meters per minute at some t, with t being greater than 5 and less than 8, and to give a reason for our answer. So if we're trying to find whether or not a velocity is going to hit a certain value, our best bet is to look at the intermediate value theorem, because we're given the endpoints of our domain. In this case, it's just 5 to 8. So remember that the intermediate value theorem states that given a continuous and differentiable function f of x will take every value between its endpoints a and b. So it'll take on every value between f of a and f of b. So in this problem, we can see that VA of t is a differentiable function, and we can deduce that VA of t is also a continuous function, because a train is never just not going to have a velocity. So we know that for the intermediate value theorem, it is differentiable. It is differentiable and is continuous. So we can use, oh, that's ugly. So we can use the intermediate value theorem. So we know that VA of t is going to take on every value between VA of 5 and VA of 8. And let me clean that up just a bit. There we go. So looking at our table, we know that VA of 5, our velocity at time 5, is 40. And then our velocity at time 8 is -120. So if VA of t is going to take on every value between 40 and -120, then it is reasonable to state that train A's velocity is going to be -100 at some point between t equals 5 and t equals 8. So because it satisfies all of the conditions of the intermediate value theorem, and -100 is smaller than 40 but greater than -120, we know that the velocity will assume this -100 value. So we're going to skip part C because it deals with the integral of a motion problem and go straight to part D, which reads, a second train, train B, travels north from the origin station. At time t, the velocity of train B is given by the b of t is equal to that expression. And at time t equals 2, the train is 400 meters north of the station. Find the rate in meters per minute at which the distance between train A and train B is changing at time t equals 2. And this part D will require a vital piece of information from part C, which is at time t equals 2, train A's position is 300 meters east of origin station. So that goes along with part D. Now, this is a related rates question because you're trying to find a rate of change when given more rates of changes. So when trying to tackle these related rates questions, it's best to have a visual so you can see the relationship between the rates, as well as listing your knowns and unknowns so you know exactly what you're trying to find. So let's draw a little map down here. So if this is the origin, or the origin station as they call it, train A, we know, is 300 meters to its east. We're given in the question that train B is 400 meters north. So 400 meters north is where train B is. And we're trying to find the rate of change of the distance between B and A, or the line segment connecting them. So this line segment. And let's call this line segment C for C squared, and call this one A, and this one B. We know that the B of t is equal to negative 5t squared plus 60t plus 25. So if this expression models the velocity of train B, we can rewrite this as the derivative of the distance, the rate of change of train B's distance from the origin. We're not explicitly given an equation for VA of t, but we're given a table with selected values, and we know that at time t equals 2, what the question is looking for, that the value of V of A is 100. And using the logic we've established in the above problem, we know that this is dA dt, the change in train A's position with respect to time. What we're looking for then is dc dt, the rate of change of the distance between B and A at time t equals 2. So now looking at our drawing, we can see that the relationship between A, B, and C is it's a right triangle. So we can use Pythagorean's formula to model their relationship. So A squared plus B squared should equal C squared. Now it's important you don't plug in numbers immediately, because if you plug in numbers immediately, you stagnate this problem. If you plug in A now and plug in B's value now, you're assuming that A and B are not changing, and therefore you're also assuming that C is not changing, when we know that these trains are in motion and there is rates of changes going on. So first we need to take the derivative of this equation. So the derivative of the right side, c squared, is 2 times c, and then we use the chain rule, so now we go inside dc dt, which should equal the derivative of a squared plus the derivative of b squared, and the chain rule applies to them as well. First we take the outside, this is 2a, times the derivative of the inside, so this is dA with respect to dt. And same thing for our b. So this is dB over dt. Now, if you take a look at your modified equation, you can see that there's rates of change inside this equation, meaning it's no longer stagnant. You've introduced motion to it, so you can start plugging in your values. So using Pythagorean's formula, we know that 300 squared plus 400 squared should equal c squared. So c is equal to 500. So over here, this becomes 1000 times dc dt is equal to this. Now we also know that a is equal to 300, so this coefficient becomes 600, and dA dt we said was 100, so this is 600 times 100, plus 2b, which is 2 times 400, which gives us 800, times dB dt, which is illustrated by this equation here. So if we plug in 2 to VB of t, we get VB of 2 equals 125. 125. So then this is 800 times 125. Now this devolves into a basic arithmetic problem. Messing around with the equation you have here, you could divide both sides by 100, or you could have done the factoring in this step above by canceling out these 2's. But either way, you get dc over dt simplifies down to 160 meters per minute. So I'm going to do something a little bit different with this, with the 2014 AP Calculus AB FRQs, and split them into two. So in this video, we covered questions 1, 3, and 4, and then in the next one, part 2, we'll take a look at questions 5 and 6. So be sure to stick around, and I will catch you in the next one.